Okay, let me introduce Andrew Collett, who will be talking about impact-generated vapor from meteoroid bombardment.
Great. Okay. Yes, I'm Andrew Collett. I work here at CU. I work at the Colorado Center for Lunar Dust and Atmospheric Studies, which is a facility here at CU Boulder attached to Laboratory for Atmospheric and Space Physics, or LASP. Let me go ahead and move to my next slide. There we go. So this is a summary of my talk. I'm going to be describing a series of experiments that we carried out here at our experimental facilities, our dust accelerator facility, aimed at determining the quantity of neutral molecules produced in a simulated micrometeoroid impact. This is part of a campaign of measurements that we've been doing over the past few years aimed at looking at all of the impact products from micrometeoroid bombardment. That includes neutral gas, charged particles, the ejecta. We have a recent paper submitted on the ejecta particles produced by micrometeoroid impact, and cratering. The experiment I'm going to describe successfully detected the gas puffs produced by impact of micron and submicron sized iron spheres. Those are our simulated micrometeorites, in the speed range of 1 to 6 kilometers a second. We determined that the scaling of the quantity of neutrals released is consistent with the power law in mass and speed of the projectile. So just some background for why micrometeoroids are appealing as a source for neutrals. They're a continuous source. Most people here know they reach all parts of the moon, including the poles and permanently shadowed regions. The physics of the impact are actually very interesting. It produces a short-lived transient gas and plasma cloud, which have estimated temperatures on the order of 3,000 to 5,000 degrees Kelvin. The plot on the right side of the screen here is actually taken from a recent paper of ours in Planetary and Space Science talking about temperature measurements over time in one of these impact clouds. And you can see that even in these relatively modest impacts, 7.4 kilometers a second and 5.9, you actually get initial temperatures on the order of 3,500 to 4,000 degrees Kelvin. We can actually watch the thing cool here. So this can liberate water from the surface, vapor form. It also produces ejecta particles that can redistribute the ice. One of the interesting things about this, not in this talk, but it's kind of an open area of research, is that over this cooling time scale, you can actually have chemical effects in the vapor cloud. So it's a whole bunch of different activities going on in the impact. Okay, so this is an overview of the experiment performed. The goal, as I said, is to measure the quantity of neutrals produced in micrometeoroid bombardment. The quantity is the easiest thing to measure. We're going to try and measure it across as wide a range as possible in mass and speed, otherwise you'll see sensitivity limits in the experiment prevent us from going all the way up to lunar speeds of 20 or more kilometers a second. Our technique will be to measure the pressure increase within a small volume. We crash these micrometeoroids into a small volume. We look at the gas that comes out, measure the pressure as a function of time, and we get the total quantity that way. The main experimental challenge is that it requires a very low background gas pressure. To give you guys an idea what that means, general lab vacuum, high quality vacuum for plasma physics experiments, for example, is 10 to the minus 6 torr. And the vacuum levels in this experiment that are required to see anything are on the order of 10 to the minus 10 torr. So the picture on the left-hand side here is a photograph of the target chamber at our accelerator facility. This is one of 2 target chambers. This one is designed for ultra-high vacuum. So I go to the next slide. So this is the source for our simulated micrometeorites. This is a dust accelerator facility which exists at the CU Boulder campus. It fires charged micron and submicron scale dust particles. We can fire anything conducting, anything that's like iron or aluminum or a thing like that, and also we can coat insulators like olivine with a conductive coating and fire them as well. The system has a design range up to 100 kilometers a second. We routinely see particles up to 60. It turns out, though, that as you can see in this distribution on the right here, that the faster particles are also smaller, and that leads to a sensitivity limit in this experiment of about 6 kilometers a second at the upper speed range. The machine is equipped with detectors that allow us to characterize the speed and mass of every particle. That means for every impact, every gas puff, we know exactly what hit the target. Not used in this experiment, but also a good feature, we have active down selection of particles, so you can dial in the mass and speed range that you want, and you only get that in your experiment. So I'll try not to bore you guys with the whole gory details of the experiment, but this is a block diagram of how the machine works. Everything in this box on the left here is part of the infrastructure of the facility. We have a dust source that charges dust particles. They're charged at a 3 million volt potential level to ground, so they're fired out of this machine electrostatically. They go down a vacuum beam line. They pass through a series of detectors. Like I mentioned, we can down select the ones that we want. Each detector feeds into a database, so we know exactly what's going into the target chamber. So the target chamber in this experiment over here is our UHV chamber with an ion gauge target. It's a small ionization gauge that measures the pressure in the vacuum system. Next slide here. So this is a blow-up of that measurement device. I won't go into all the details of how it works, but basically you have a dust impact, dust comes in, it strikes the rear housing of the gauge, the stainless steel flange on the gauge there, and you get a gas puff, and the gas puff goes in and fills the gauge housing. And so the way it works is there's a filament here, which is emitting electrons, which are accelerated from the filament into this ionization volume here, and they in fact ionize a fraction of the gas molecules. And so you have a bunch of ions now that are floating around in here. Their density is proportional to the density of the neutrals. And there's a thin wire in the center of the gauge, and it just collects the ions. So you have 180 volts on the grid here on the ionization volume, and a thing here it's at 0 volts. And so the ions go to the wire, they're neutralized, and you get a current. So the output of this experiment is basically a current versus time, and the current is proportional to the instantaneous density. And so the derived quantity in this experiment I'll be talking about is actually the total amount of charge, which is proportional after some math to the total number of neutrals that are released. And you also get a time scale. This is how long the gas hangs around in this volume before it's lost to the vacuum system or it sticks to the walls. So the outputs, again, are total charge Q and the duration of the measurement T. So this is what you see if you do a whole bunch of these experiments. This is two calculations on this graph. First of all, the x-axis is the mass of the incoming projectile. This is in kilograms. And the y-axis here is the total charge that's recorded on the ion gauge. And the two calculations here are basically all the things we fired at it. We did 2 runs, one with the gauge turned on and working and ionizing the neutrals. That's the open circles, the black ones, and one with the gauge set up in just the same way, only no primary electrons, and so you don't get ionization. So this is basically a control. The blue points are a control for the experiment. Basically, unfortunately, my math didn't make the trip, but the idea is that the quantity here is a time-integrated density, and so you actually see on the right-hand side here, you have time-integrated density, meaning it's the total number. It's a number density, so it's so many particles detected, integrated over the length of that experiment. And so we do some unfolding to pull out the total number of neutrals, which we want. So there are a couple different things in this experiment that I'm going to mention. First of all, you have to assume you know the ionization efficiency. We're going to assume that all of the gas molecules we've released are basically N2, because that's what the gauge is calibrated for. It's not too bad an assumption. You have, for example, water here is 2.2 at this energy, and N2 is 2.5. All the way up to the alkalis, potassium and sodium, that are higher in 3.5, 5.5 range. About a factor of 2 from the lowest to the highest. We also know a couple different things. We know the volume of the ionizer region, and we know the length of time from our data. And so basically, we take the number of neutrals, we take that time-integrated density, divide by the time scale, and multiply by the volume, and we get a total number of neutrals that we observe. So the result here. So what I've done, this is the same plot before, total charge, like I saw before, still versus mass, and number of neutrals on the y-axis here. And so if you look at it, it looks like it's basically a factor of 2 over many decades in mass. So at first glance, it looks like it's constant, right? But unfortunately, it turns out, or fortunately for us, it turns out that in these kinds of accelerators, the mass of the projectile and the speed are not independent. It turns out that the lighter particles go faster, a lot faster. And so this is the distribution with all the particles in the experiment between mass and speed are impactors, and you can see that it basically follows the power law. And so what happens in these experiments, and it happens, the classic example is experiments looking at impact-generated charge, is that the distribution of the incoming particles actually masks the dependence of the phenomena you're looking at. For example, impact charge experiments is actually a power law, in the amount of charge released in the mass and velocity of the impactor, and that is not immediately apparent in the charge data. And so one question that we can ask with this information is what happens, there we go, what happens if we assume that the quantity of neutrals released is proportional to the mass, and then we plot that as a function of the speed. So we normalize out the mass. And if you do that, you get this. So the y-axis now is n over m. It's the gas molecules per unit mass, and the units are kind of funky there. And this is versus speed now. And you can kind of see a power law starting to develop. And so if we go to the next slide here, if we model this as a power law, and we say it goes like m to the alpha v to the beta, and we assume that alpha is 1, we're dividing by m, then you can actually fit a line to it, and you get the velocity dependence is roughly v to the third. And so you can skip to the next slide here. So this is the same plot. So this is our power law, our consistent power law for the quantity of neutrals. And what I've done now is change the scaling of the axis to, on the right-hand side here, be fraction of the projectile. So remember that the quantity we get is total number of particles. The ion gauge can't tell you what the mass fraction is, what the species is. All it tells you there's a certain number of ions that are observed, and you interpret that as meaning a certain number of neutrals that are observed. And so what I've done is I've normalized this to the number of atoms in the projectile, and so this is a number fraction of the projectile. And what you can see here is that in our range that we've measured, roughly up to about 6 kilometers a second or so, there we go. So the gas released is about 0.1% to 5% of the number of atoms in the projectile. And I stress that this is not necessarily atoms from the projectile itself. It means that you have some vaporized atoms. It also means that you have some things from the surface of the target, adsorbed gases that are being released, and so forth. So it's total quantity of neutrals liberated in the impact. And so this has implications for, on the moon, for example, for the effects of secondaries. You get ejector fragments from impacts, and there's a huge range of speeds. Some of them are even faster than the original impactor. But if you have fragments that are going in a lower speed range, they actually have a surprisingly high efficiency, 5% or more at 6 kilometers a second or so. We can make some extrapolations here, although it's extrapolating over about a decade. We can go up to the speeds, the average speed of the moon, the 20 kilometers a second or so range. And this model predicts roughly complete vaporization, which is encouraging, or at least the total amount of gas release is consistent with 100% of the particle. So if we go to the next slide here, I want to highlight some of the conclusions here and talk about some of our future work. So we accomplished what we set out to do, which is to measure the total quantity of neutrals. And it's consistent with the power law, if you model as a power law, with linear in the mass and with roughly cubic dependence in the velocity. And if we go there, so there's a number of open questions that we're working on at the moment in our laboratory. The obvious ones are, can the power law behavior be confirmed? There are ways to work around this power law behavior in the mass velocity distribution. It's been done, for example, for light flashes. Light flashes also follow the power law in the impactor mass and velocity, the intensity of the flash. And there are a series of experiments that do that basically by broadly expanding the data set. So you have many, many particles outside that line. What is the behavior at higher speeds? I mentioned the sensitivity limit. If you look at this experiment over here, this plot with the total charge, you'll notice that the lighter ones, here we go, you'll notice that the lighter ones, the control and the experiment groups go very close together. We're nearing our sensitivity limit, which is about 5-10 pentacoulombs of charge on the amplifier. And so one of the things that we hope to do is increase sensitivity to see if we can look at the faster particles and see whether or not this behavior holds. Composition. Can't tell composition from the ion gauge experiment. We want to measure that with a residual gas analyzer and see what's coming out. And finally, of course, the moon, as far as I know, is not made of stainless steel. So we need to use more realistic analog targets, including minerals. I'd love to do regolith if we can get into a huge feed chamber and actually do that experiment. And last thing I want to show, of course, is that the lunar talks, and I have to show Laddie. Looking forward to the actual measurements that it'll be performing on the trace species. This has been meteorites have been proposed as a source for the more exotic elements in the exosphere, things like silicon and oxygen and so forth. And we'd love to see whether LIDI can reduce the upper limits or make a measurement on those species. So with that, I'm going to conclude, and I can take your questions.
All right, very good. We do have a question. I just want to let Georgia, I think you're up next, so why don't you get your webcam started. Michael Poston has a question. Do you think your vapor is coming mostly from the steel target or the particle itself?
Great question. I don't know. I can tell you that that for our other impact experiments, the theory predicts complete vaporization of the particle starting at around 10 kilometers a second. And so I imagine it's probably a mixture of some of the material from the projectile. It's iron, remember, so the iron I imagine would stick to the gauge walls. But I imagine it's a mixture of that and also adsorbed gases and alkalis from the gauge.
Okay, Yang Lu says, nice experiments. Interesting to see it is less than 5% volatile loss. Following Michael's question from micrometeoroids of carbonaceous chondrite composition, hypothesis suggests complete vaporization of the meteoroid at 5 km per second impact velocity. I wonder how this compared to your experiment results. Great
question. I mean, I don't know. I'd love to do the experiment with a coated insulator dust grain apart from cell and iron and see what the result is.
You know, a question I had was, you know, you also generate a plasma when you do these impacts. Was the mass of the neutrals greater than the mass of the plasma, or comparable, or is it something you need to look at?
The number released, as I understand it, is roughly 10 to the 8th neutrals coming out in this experiment, and I believe in comparable experiments for the charged particles that are emitted when the plasma goes away, it's about 10 to the 5. So maybe a factor of 100 to 1,000 times more neutrals than the plasma.
All right, that's very interesting. That's good to know. All right, good.